Hello dear students, in this lesson we are going to talk about the scientific notation. It's also called the standard form of a number. In our IBDP, it's just the first topic and it's a very simple topic. We don't have to emphasize much on that, but just because we have to cover each and everything, so I'll be explaining each and every topic in detail. So let's begin with scientific notation. Students, why do we need this method? See, sometimes we have to deal with extremely big or small numbers. They may have a lot of digits. So to make it compact, we have to follow a specific format, which is a times 10 raised to the power of k. We'll discuss about it a bit more, but this is the format in which we have to represent any number in scientific notation. We can have different examples, let's say 3 times 10 raised to the power of something, let's say 10 raised to the power of 5. It could be 2.7 times 10 raised to the power of 20. We can even have 3.689 times 10 raised to the power of 49. It can even have a negative sign. The exponent may also have a negative sign. Students, you see, no matter what exponents we have over 10, but if we focus on the first digit here, like first number, there is some speciality in that number. That number is always greater than 1, and it could even be equal to 1, but it's always less than 10. And that's the main method that we have to follow in the scientific notation. Okay, now you can see one thing. The number can either be equal to 1 or even it can be greater than 1. But it's always less than 10. Why is it so? Why it can be equal to 10? Just because the students, whenever we have, let's say 10, and then we have another exponent of 10, let's say 10 raised to the power of 5, so this itself will actually be combined, and we can further have, with the law of exponents, we can have 1 plus 5, that is 10 raised to the power of 6. And that we don't want. We want a specific format, and that format will no longer be present if we have 10 itself to be multiplied. In our real life, we have many examples in which many situations in which we have a very big or very small numbers, just like protons, their speed, their diameter. Their diameter is pretty small, and if we just go to write in meters, centimeter, we'll have to put a lot of decimal digits in that. Similarly, speed of light. If we want to represent it in meter per second, it's a big number. So to overcome that situation, to shorten those digits, we often use scientific notation, and we'll discuss different methods in which we can do that. Let's begin with numbers which are very big. Okay, so numbers which are very big are, or obviously it can be even very small or even a simple number as well. That's still okay. So if the number is larger than 10, there is a specific method that we have to write. Basically, whenever we have any number, if there is no decimal present in the number, we imagine it to be at the end of the number, right? Let's take an example first. For example, we have 35. So if there is no decimal present, and of course it's greater than 10, so the rules that I'm gonna tell you here will be applicable on all those numbers which are greater than 10. So let's say if it's 35, so what you can do, students, you can imagine that, okay, decimal lies at the end, right? It's too tiny. Let me just make it thicker. Yeah. So decimal exists at the end of the number. Now, in order to write it in the standard form, we want to format a times 10 raised to the power of something. So we want the first number always to be between 1 and 10. So what we have to do, we can shift the decimal towards left side by 1 digit. And as soon as we shift the decimal, the number becomes smaller. To compensate that, what we have to do, we have to multiply an exponent of 10. Just because we have shifted the decimal by 1 digit, so it will be just 1 as an exponent. So equality is still maintained. If you multiply 10 to 3.5, you will still get 35. But this is the standard notation or scientific notation of the same number. Let us take the next number. We've got 3 digits in that, and still we don't have any decimal present in that. So what we can do, we can imagine the decimal to be at the end. Again, this time we need to shift the decimal to its left by 2 digits in order to make the first number between 1 and 10. So this time we can write the number as 1.46, and just because we have shifted the decimal by 2 digits right now, we have to raise an exponent of 2. So it's 10 raised to the power of 2. This is the special symbol that I use for multiplication, so don't worry about that. You can still use an X. That's still okay. Alright, now we got such a big number here. It's 65,000. Not very big, but it's considerable. So 65,000. Okay. Again, if there is no decimal present in the number, you can always assume it to be at the end. Now students, we have to shift the decimal by 1, 2, 3, 4. Just remember a trick that you have to keep first digit, and then just after that you need to keep a decimal, right? So that's a simple trick, but the idea is the first number has to be between 1 and 10. So it's possible if we can keep it as 6 point something, say 6.5. Okay, so we're going to keep it as 6.5 now. And now it's not needed to keep those zeros here because trailing 0 doesn't matter in decimal number. So we can just keep writing those zeros. Or if you want, you can still do that. Now, just because we have shifted the decimal by 4 digits to the left, we simply have to raise an exponent of 4. So even if you just try to simplify, it's nothing but 10,000. And when you multiply 10,000 to 6.5, you will get your number back. But we don't want to do that again. It's of course we are writing the number in the scientific notation. So this is the second example, third example of that number. Now we have decimal already present in the number. So as you see, 78.65. So in order to make this number between 1 and 10, we need not to shift the decimal by many digits. It's just 1 digit is sufficient. Means if you shift the decimal by just 1 digit, if we keep it between 7 and 8, that will fulfill our goal. So here we can write it as 7.865. No matter how many digits are present in that, we only have to notice how many digits we have shifted the decimal. It's just 1. So you would apply 10 raised to the power of 1. That's it. This is such a big number. Okay, we have got 8 zeros in that. 3 followed by 8 zeros. 1, 2, 3, 4, 5, 6, 7, 8. And that's where you can understand its significance. So we can imagine the decimal to be here. And now if you wish to shift the decimal to its left, basically you have to count those 8 zeros. And then you have to shift the decimal here. Now you can even write 3.0. It's useless to write all the trailing zeros because that doesn't matter. So 3.0 times 10 raised to the power of 8 because we shifted the decimal by 8 digits. So these are a couple of examples of big numbers. Let's take examples of a couple of smaller numbers. We still have to follow the same format that the number has to be between. That means the first number in the format of a times 10 raised to the power of k. So the a has to be between 1 and 10, where a cannot be equal to 10 because as it becomes equal to 10, it will further be combined with the exponential term that we don't want. Okay, so I already have got some examples here. Let's continue with this. Now students, to make this number between 1 and 10, we want to shift the decimal but not to the left but towards the right. We have to shift the decimal towards the right direction like this. Okay, so as soon as we shift the decimal towards the right direction, yes, it's 1 and we can write 1.0, right? Because I shifted the decimal towards the right side, and just because I shifted 1 digit only, so I have to apply an exponent of 1, but make sure to apply a negative sign because we tried to make a smaller number as a bigger number. See, 0.1 is smaller and 1 is bigger comparatively. So to compensate that, we need a negative exponent. Let's take the second example. It will be clear from there. we've got 0.045. So in order to make this number between 1 and 10, we have to shift the decimal towards right side by 2 digits, like 1 and 2. So now we get, okay, it's 4.5. Initial, like leading zeros, we don't have to write, okay? It's 4.5. And just because we shifted the decimal by 2 digits, we have to raise an exponent of 2, but make sure to apply a negative sign. Okay. One more example, students. It's 0.00607. To make the number between 1 and 10, we have to shift the decimal towards right side by 3 digits. So this time we get 6.07 times 10 raised to the power of negative 3. This because we shifted the decimal by 3 digits. Now let's try to understand how do we operate many numbers which are already in the standard form or in the scientific notation. So students, we'll have to first of all recall a few rules of exponent. They are very simple rules. Let's say we have x raised to the power of m times x raised to the power of n, means the same base is there and we have to multiply two exponential terms. So we can add their exponents like m plus n. We have to write the base only for a single time and then we can add the exponents. In the same manner, if the two terms are in division, having the similar base, exponents may be different. This time you can write the same base for only once and then you need to subtract the exponents. There is another law where we have exponent of an exponent, let's say x raised to the power of a, and again we have a whole power of b. We can multiply that power, a times b. And just one more rule is there, like there are many rules of course, but here we'll be utilizing those rules. Let's say we have multiple terms multiplied and we have got a common exponent, let's say m. So we can distribute the exponent equally, like we have to apply the same exponent over each and every term if the terms are in multiplication. But make sure this rule is applicable only if the terms are either in multiplication or in division. It's not applicable if the terms are in addition or subtraction. So if the terms are in just multiplication or division, yeah, we can apply this rule. Okay students, we are good to go now. We can continue with that examples where we have to perform operations between two or more numbers which are already in the scientific notation. Let's begin with the first question. Every term is in multiplication, students. The good thing is you can first multiply non-exponential term together with the non-exponential term and then exponential term together with the exponential term. So yeah, that's simple. We've got 10 raised to the power of 3 times 10 raised to the power of 4. Okay, so you know that the same rule I have told you. When we have the same bases, we can write them for once and then we can add the powers. So it's 3 plus 4, that's going to be 7 of course. And we can multiply 4.5 and 2.1. That's pretty simple. I'm going to use a calculator to multiply. You can even do it manually if you want. We get 9.45. This number already lies between 1 and 10. Let's suppose if the number wasn't lying between 1 and 10, then we would have further simplified it. But right now it's okay. We've got 9.45 and this is an exponential term. So 9.45 times 10 raised to the power of 7. And that's your answer. The question, like answer, is already in the standard form because the first number lies between 1 and 10. Let's take the second example. In this question, we have a whole exponent and in the bracket we have two terms multiplied. So students, we have to apply the same exponent on both the terms actually. Okay, we can rewrite the terms and we have to apply the same exponent here as well as here. Now the first number will be squared. As we square it means we multiply 3.2 to 3.2. We get 10.24. At the same time, we have got exponent of exponent. And students, when we have a power of power or exponent of exponent, we have to multiply them. So it becomes negative 2 times 2. So we can write it as negative 4, 10 raised to the power of negative 4. Here the number we have, students, is 10.24, which is not between 1 and 10. It exceeds 10. So we want this number between 1 and 10. So to do so, what we do, we shift the decimal towards left side in order to make it between 1 and 10. So it becomes 1.024. Let me write down 1.024. But students, just because we have made bigger number as small, we have to balance that by multiplying an exponent of 10, just like we used to do earlier. And just because we shifted only by one digit, we add an exponent of 1. Now we already had 10 raised to the power of negative 4. But now, students, we have to simplify these two exponents together in order to give the answer in the scientific notation. So no problem, we have the same basis, the powers get added. We get 1 and then negative 4. 1 plus negative 4. We simplify that and we already have 1.024 here. We get finally 1.024 times 10 raised to the power of negative 3. This is your answer in the scientific notation or in the standard form. Let's take the third example. Students, here we have terms in division. So we already had the rule. So first of all, these two terms can be simplified separately. As I divide 3.5 by 7, I get simply 0.5. Okay, I can write down this is 0.5, whereas the terms which are having power, we can apply the law of exponent. When the powers bases are similar, we have to simply subtract the exponents. We get 10 raised to the power of negative 1 here. But over here, students, again you notice that this number is even less than 1. We want this number greater than 1 and less than 10, or even equal to 1. So to do so, what we do here, we have to shift the decimal by one digit to the right direction. In that way, students, we get 5.0, and in order to balance that smaller number and bigger number, we need to multiply an exponent of negative 1, 10 raised to the power of negative 1. We have to solve it for one more step. Here we have to simplify 10 raised to the power of negative 1 times 10 raised to the power of negative 1, and that's simple. We have to again add the exponents because the bases are same and the terms are in multiplication. So negative 1 plus negative 1, and finally we get 5.0 times 10 raised to the power of negative 2. So this is your answer. We'll continue with the fourth example. Students, here the terms are getting added, so we cannot apply those laws of exponents directly on that. We need to do something else in that, and we can do it wisely using some technique. First of all, you can notice here we have an exponent of 10 raised to the we have a term 10 raised to the power of 3. Here we have 10 raised to the power of 4. We cannot directly add them. If the terms were similar, we could have taken them as common, but we can do that, students. How can we do that? The one way, you first simplify it as usual. You simplify as a standard, like as a simple number like 5,000, and it's something like 2.4 times 10,000, and you simplify and add. We don't want to do that. We have a special method. It's up to you what method you want to apply. Either you can do it directly, like first you convert them into the simpler numbers, add them, and then further convert them into the scientific notation. Or from the beginning itself, what you can do, you can convert them in a specific format. How to do that? Let me tell you. See, this is 10 raised to the power of 3. In order to make it 10 raised to the power of 4, we can have something. What we can do, see, we have 10 raised to the power of 3 here. If we can multiply 10 here, like we multiplied 10 and we divided 10, means we did nothing. It's just 1 only, right? So we are allowed to do that. It's just we can multiply 1 to any number, that doesn't affect at all, and keep the second number as it is. So what happens here, students? The numerator becomes 10 raised to the power of 4, and we can bring this 10 underneath 5. So I can write down it as 5 over 10, and 10 raised to the power of 3 times 10, it's a kind of 1, so it simply becomes 10 raised to the power of 4. And here we have 2.4 times 10 raised to the power of 4. So you can consider it to be 0.5 times 10 raised to the power of 4. One moment. And here also, students, we have 2.4 times 10 raised to the power of 4. Now you can notice that we have got the same term in both the terms. We can take them as common. So as we bring it as common, we can write here itself 10 raised to the power of 4. We get 0.5, and here we got 2.4. We can simplify that. We get 3. 2.5 plus 0.5 is 3.0. So finally we've got 3.0 times 10 raised to the power of 4. And yes, the number is already between 1 and 10, so we need not to do anything else in that. And this is your answer. I hope it's clear. Let's continue to the next question. Sometimes we may have to deal with a few word problems. Again, the idea is we need to follow laws of exponents, and sometimes they might give you a specific situation, a specific formula in which you have to plug in the numbers. Just like here, they're given a formula. It's energy conservation, something like that. Okay, E equals mc squared. Now they're given the values of m, that is mass, and c, that is speed of light. So they want us to figure out the value of E, that is energy of a proton, where m and c, both the components, are given. So basically what question wants you to do, the question wants you to substitute the values of m as well as c in the given equation, and then apply laws of exponents and then solve that. That's the basic idea. So no problem, students, we can do that. So first of all, we have E equals m times c squared. So in that format, we have to write the formula. Now the value of mass, that is m, is given to you as 1.67 times 10 raised to the power of negative 27, whereas the value of c is given to you as 3.0 times 10 raised to the power of 8. Okay, no problem. And now, students, it's squared, so you have to make sure to square it like this, and now you have to apply laws of exponents that we discussed earlier. Means we have to distribute the exponent on both the multiplied terms first of all. So we can do that. We can apply it on 3 as well as on 10 raised to the power of 8. So 3.0 or just 3, it's still okay. And this is 10 raised to the power of 8. We keep the first term as it is. We can further simplify that. We got 1.67 times 10 raised to the power of negative 2. Here we have 9. And over here, as you know, the powers get multiplied when they are applied back to back. So that's going to be 10 raised to the power of 16. Now, students, you know what to do. You have to keep the exponential terms together and the non-exponential terms together to multiply. That's simple. 1.67 times 9, and again we can have 10 negative 2 times 10 raised to the power of 16. We can simplify that. I can use a calculator to do that. We get 15.03. Over here, when we simplify that, we get negative 2 plus 16 will become positive 14. I'm directly writing here. But again, students, we are still not done. We want to get the answer in the scientific notation. So in order to do that, we have to shift the decimal towards left by 1 digit. So immediately we have to add an exponent of 1 here. And we already had 10 raised to the power of 14. So further, we have to combine these two terms together, and finally we get 10 raised to the power of 1 plus 14, that is 10 raised to the power of 15. And that's your final answer for energy. And you have to give the answer, they might ask you to give the answer in joule. Joule is the unit, or you can even have some formula based unit as well. But to be correct, to be accurate, you can write that according to your question. They asked you to give the energy in joule, means J is the unit, means joule is the unit, of course. Okay, so this is how we simplify numbers in scientific notation. I have a couple of more examples. Let us now focus on that. Okay students, again, similar situation, we are given a formula. We also have been given values to plug in, and we have to simplify that. We have to get time, T for time, D for distance, C for speed of light, and this is a very well-known formula, relation between speed, distance and time. So no problem, we can write that. The time we have to figure out, and the distance given to you is this one. They're given the distance between the sun and the earth is 1.5 times 10 raised to the power of 8, and the speed of light we are given as 3 times 10 raised to the power of 5. Make sure if the unit of the distance and speed are same or not. Distance is in kilometer and even speed is also in kilometer per second, so there is no problem. You have to ensure, if it was suppose in meter or something else, you would have converted them into similar units, but right now that's not the case. No problem students, we have got the same situation. We have to simplify those terms separately. This is the non-exponential term, this is the exponential term. We have to solve them separately. As I divide 1.5 by 3, I get 0.5. Over here I have 10 raised to the power of 8 negative 5. We're still not done because the leading number we have here isn't between 1 and 10. So to make that, we have to shift the decimal by 1 digit, and in that way we have to compensate that with an exponent of -1, because now we made a smaller number into a bigger number, so that can be compensated by multiplication of a negative exponent. And we already had another exponential term, so we have to simplify that. Finally we're going to have 5.0 times powers get added based on the laws of exponent. We get 5.0 times 10 raised to the power of 2. And again, just because it's time and the unit was given in kilometer per second, so the time has to be in second only. So 5 times 10 raised to the power of 2 seconds. And that's the answer. I hope it's clear. Okay, they also asked you to get the answer to the nearest minute. It's almost 500 seconds, of course, right? So time can either be 500 seconds, and you know, to convert seconds into minute, you have to divide by 60, and as you divide it by 60, you get about, one moment, around 8.3. So nearest meter we have to write, you will again be taught approximation, so approximately it's equal to 8 minutes. So that's your answer. That's it in this question. Let's continue to the next question. This could be the last question of this lesson. Here students, we have been asked to get in this question we have been asked to find out the difference between population or people, whatever it is. They're given two numbers, okay? Population of the German cities, these are the two cities, and in different cities we have different population. Of course this is a big number, so the one way you first convert it in the simpler number and then subtract and you will get your answer. But the better way is, if you have to simplify that, you can write them in the way that they have a similar exponential terms, and then by taking something common it will be easier, we'll have less work. Okay, one more thing, students. Here we have 10 raised to the power of 6. Here we have 10 raised to the power of 5. Of course the first number is bigger because it has a bigger exponent of 10. So keep the first number here, 1.43 times 10 raised to the power of 6, and we need to take away this number, 7.76 times 10 raised to the power of 5. In order to make them as a similar exponent, what we can do, here itself I can do one thing. I can multiply by 10 and I can divide by 10. Just it's a trick so that we can do it very easily. We get 1.43. The first number is as it is. Now do one thing, bring 10 down here underneath 7.76, because 10 over 10 is nothing, it's just 1, right? And we are of course allowed to multiply 1 to any number. That won't affect that. But the advantage of doing this is this also becomes 10 raised to the power of 6. So now we have a kind of situation where 1.43 times we have a number 10 raised to the power of 6 here, and the same exponential term we have even here in the second term. Of course this can be simplified. Now students, what we can do, we can take it out as common, as we keep this term in the bracket, and we have taken 10 raised to the power of 6 as common, and we have got 1.43 here, negative 0.776, and of course this can be easily subtracted. I'm gonna subtract it. We get 0.654. Again students, we need one more step in that question because we want to get the answer also in the scientific notation, or we can even directly write, because they did not ask you to give the answer in the scientific notation, so it's still okay. You can do one thing, you can directly represent the answer in the form of number of people. Here we have actually 10 raised to the power of 6, so 1, 2, 3, 4, 5, 6, and accordingly if you multiply, 3 digits are compensated by 3 zeros, and we have to add 3 more zeros. So this many people, 654,000 people difference is there in 2 cities. So that's it students. I hope it's clear to all of you. See you in the next lesson.